Lazy iterators in Python. They're particularly useful when you're iterating over a large amount of data. So it's implemented using a generator expression denoted by parentheses with the dots representing the actual logic. Generator expression is similar to a list comprehension. So let's have a look at the key points. It's lazy evaluation. So the values are generated one at a time as the iterator is iterated over, instead of actually creating a complete list in the memory. Similar syntax to list comprehensions. So if you know a list comprehension, you should quickly pick up a lazy iterator. So there we go. X squared for X in range 5. For value in lazy iterator, print value. So the iterator needs to actually be processed, so to speak. You can also use the lazy iterator with filtering. So you put the if condition inside the parentheses after you've done the X for X in numbers. The lazy iterator generates only the even numbers from that list of numbers because it's using modulo 2. Remember, lazy iterators can be particularly beneficial when working with large data sets because they actually generate the values on the fly rather than storing in memory. So they've got advantages, but also there are disadvantages. Let's just compare them. So memory efficiency with a lazy iterator, they're very efficient for streaming data, better for infinite sequences. They do have a performance for small data sets, so a performance issue for small data sets because you might actually be better off with a list. Easier to debug. List comprehensions can be easier to debug because you can actually see what you've got in your list because the iterator is generated on the fly. So use cases, lazy iterators, use them when dealing with large data sets. There we go. And there's the example. So let's actually run the example. Okay, so lazy iterator, x squared for x in range. I'm putting in a big number here, so that's 10 to the power of 7. So that's 10 million. I found through testing that that was about the best number to do the demonstration with. Start time, so we're measuring a time, so I've imported time. And we're just basically saying end time equals time dot time. Then we subtract the start time from that to give us the lazy iterator time. So then we'll print the time taken. We'll also print the lazy iterator. So if I hadn't put this on the end, I would end up printing, and I've tried it, trust me, I've printed virtually 10 million numbers. So don't do that. If you're going to be printing, make sure you do have your conditional logic at the end. So if we've just run that, time taken for lazy iterator, and that is 0.0 with 4 zeros and then 22 seconds. And that's the answer. So it's returned 144 because that's if x equals 12, then square it, return it, and then print it. So that is the lazy iterator. And we have to put it in a list at the end to actually get the value. So this line here is what is giving us the 144 in the square brackets. Okay, so let's just compare that against the list comprehension. So we're doing the same thing again. Start time equals time dot time. Squares list. So we'll do the same as we did before. Really, the only difference is actually the square brackets rather than the parentheses. End time equals time dot time, same as we did before. LC, so we've got a variable called LC, list comprehension. End time minus start time. We'll print the time taken, and then we'll print the value returned from if x equals 12, square it. So we should end up with 144 as well. So the same result as we got from the lazy iterator. And what we'll do here is we'll take the lazy iterator time. We'll also take this comprehension time, and then we can see the multiple, see how many times quicker the lazy iterator actually was. So if we run this, the lazy iterator is 0.0, all those zeros 4 seconds. So is that 100,000th of a second? The list comprehension, 0.3 seconds. So the list comprehension took 98,000 times 98,346,000 times longer. Now, that's not particularly drastic with this, but if we kept on pushing that number up, so I think it will fall over even if we go up to, say, 10 to the 9, which is that billion? The lazy iterator is okay, but when you try and use the list comprehension, it gets stuck. I think the operating system actually complains. When I was testing it before, it actually kicked off at about 17 seconds. So I don't even know if this is going to complete. So if I just do Control C there, and it's frozen on me because it's using up all of the resources. So there we go. Right, if I just change that back, and then we'll run it again, 10 to 7. Now if I run it again, just happy days. And that time it was 66,000 times quicker using the lazy iterator. So